Welcome to qnawire.
This is problem number 34 of the Stewart Calculus 8th edition, section 2.8. Part A. If f of x equals x plus 1 over x, find f prime of x. So let's use the definition 1 for the derivative. This is the limit as x approaches a of the function f of x minus f of a divided by x minus a. Okay, our limit will be f of x, x plus 1 over x minus the function evaluated at a plus 1 over a, all divided by x minus a. Okay, our next step will be to multiply by the lowest common denominator to eliminate the fractions. So ax over ax. So limit as x approaches a of x times ax squared plus 1 over x times ax, a minus a times ax, a squared x minus 1 over a times ax minus x all over x minus a times ax. Now we can group some of the terms in the numerator. Let's group the ax squared and the a squared x term. Let's factor out that ax, and we're just left with x minus a. And then the remaining terms are minus the quantity x minus a. And all of this divided by x minus a multiplied by ax. Now each term in the numerator has an x minus a term that can cancel with the x minus a in the denominator, and that leaves us with ax minus 1 divided by ax. As x approaches a, this becomes a squared minus 1 divided by a squared, or 1 minus 1 over a squared. And if we generalize this for any a value in the domain of the function, given as the domain being any number x, then our derivative is 1 minus 1 over x squared. So a squared, x squared, it refers to the same derivative function. So we've concluded the derivative of this function is 1 minus 1 over x squared. Now, we're going to use the graphs of f and f prime to confirm that the derivative of this function, x plus 1 over x, is indeed 1 minus 1 over x squared. So here are the two functions plotted on the same graph. The blue is the original function, f of x, and orange is the derivative function. If we look at the blue function, we see that there are straight lines here. So this straight line will have a constant slope, therefore a constant derivative, because the slopes of the tangent lines are constant. So that's what we see here on the derivative graph. It's a constant value, exactly equal to 1. So it's constant until it reaches a point where the slope begins to change a little bit. And then we have a local maxima, which has a slope of 0. So that's what we see here, constant slope. And then it decreases to 0. And then afterward, we have a very sharp decrease in the slope of the tangent line, so very negative slopes. And the slope derivative function shows very negative slopes as we approach 0 from the left. As we approach 0 from the right, for this function f of x, we see that the slopes of the tangent lines are very, very negative. So this continues on to the right of 0, very, very negative slopes until we reach this local minimum, which has a slope of 0. is consistent with this derivative function, and then afterwards the slopes increase until the slopes become constant once again. So this derivative function is definitely consistent with our um, original function and confirms that we computed the derivative function correctly.